Today, we're going to talk about the patterns we see regarding objects in the sky. We talked about the basics of this in the Seasonal Skies lecture, or the material we covered in the planetarium if you're a Pensacola campus student. But we're going to go a little more into depth with this lecture. We're primarily focusing on how constellations work, how stars are named, and the brightness of stars, referred to as a star's magnitude, and patterns we see with planets. Humans have watched the skies for millions of years. Surprisingly, people who lived hundreds or thousands of years ago actually knew a lot more about the night sky than most people today. Think about it. Most people would struggle to come up with the names of even a few constellations because in modern times at night, we usually sit inside and watch Netflix and play with our phones rather than watching the sky. Before the invention of electric lights, people spent time watching and learning about the patterns in the sky. The same constellations appear at the same time each year, and planets follow predictable patterns. We'll look at these patterns and several others in this lecture. Earth rotates on its axis. This rotation takes 24 hours and is the cause of the day and night cycle. Earth also revolves around the sun. This revolution takes 365.25 days and is the length of 1 year. We ordinarily think of the year as only 365 days. The extra quarter of a day is why we have leap year every 4 years. It doesn't take exactly 365 days for the Earth to go around the sun. It takes about 6 hours longer, but added up over 4 years, we get 1 extra day. To start learning the night sky, you have to go outside and find north. This is important because the North Star, Polaris, is the one star that does not appear to move in our sky. The stars aren't really moving around us, but they appear to do so because of Earth's rotation. Earth's axis points almost directly to Polaris, and as Earth rotates on its axis, Polaris remains fixed while the other stars circle around it. Stars always rise in the east and set in the west, since Earth rotates from west to east counterclockwise. The stars near Polaris seem to trace a circle around Polaris, never quite setting. In Pensacola, Polaris sits 30 degrees up from the northern horizon because we are located on latitude 30 degrees north. Now don't get up and north confused. If we were standing on the North Pole, the North Star would be directly overhead. But since Earth is tilted and Pensacola is at 30 degrees north latitude, we see Polaris 30 degrees up from the horizon. An easier way to find Polaris is if you can spot the Big Dipper asterism. The two stars that form the front of the bucket point a line straight to Polaris. Remember though, as the time of year changes, the orientation of the Big Dipper will change. So you won't always be pointing down and to the left. This is what you would see if you went outside in May. The Big Dipper's two pointer stars point down and to the left toward Polaris. But if I rotate my screen around 90 degrees, this is what we would see 6 months later in November, with the pointer stars pointing up and to the right. Only Polaris remains stationary in the sky. It's in the same location all night long and all year round. If you were to take a long exposure picture or take a video of the sky and watch it on fast forward, this is what you would see. Polaris is the dot in the middle, and the other stars make streaks called star trails as they appear to travel around Polaris. Since the Earth turns from west to east, the sky seems to move from east to west. So if you want to look at something you know is in the western sky, you'd better look right at sunset before it disappears from view below the horizon. Once you've found north, you need to know what to look for. It will depend on what time of year it is. You will need an app or a sky map. And here you see a picture of a sky map. Notice the Big Dipper is pointing slightly up and to the right, like we looked at just a couple of slides ago. This map is probably for November. Also see that the constellation Orion is also visible, and he's only visible in the evenings during the winter months. If you wanted to see the constellation Hercules during this time, you'd be out of luck, as he's not up at this time of year. Now, so far, I've mentioned a few constellation names, but let's talk about where these names come from. Many of these star patterns were drawn by people long ago after their gods, animals, and heroes. Some of the pictures you see make sense, others not so much. Here you see two constellation drawings, Scorpius the Scorpion and Sagittarius the Archer. Scorpion makes sense to me. I see his head, his long body, and his curved stinger. The dots representing the stars match up pretty well with the drawing. Sagittarius, on the other hand, doesn't make a lot of sense to me. Let's play dot to dot with part of it, though. Connecting some of Sagittarius's stars, we get a teapot-shaped asterism, and the rest of the stars surrounding it don't look like someone doing archery to me. But there are alternative ways to connect the dots. And remember that a constellation is just an area of the sky, not the shape of the dot-to-dot picture. As I mentioned in the Seasonal Skies lecture, the zodiac constellations you find in horoscopes are 12 constellations that the sun seems to pass through. From the perspective of Earth in this photo, the sun is in Leo, meaning that from Earth, it looks like the sun lies within the borders of constellation Leo. Later in the year, the sun would appear to be in another constellation as Earth has moved along its orbit around the sun. One problem with horoscopes is that there really aren't 12 zodiac constellations. There are actually 13. One constellation, called Ophiuchus, is ignored and doesn't appear in this diagram, though it should, right where this arrow is pointing. Remember, the ecliptic is the path that the sun and other planets seem to follow around the Earth. The plane of the ecliptic is a flat-ish disk around the sun where all the major planets of the solar system orbit. Notice in the smaller picture it shows that the plane of the ecliptic, as compared to the plane of the equator, is tilted. Earth is tilted at about 23.5 degrees. There are 88 constellations. Remember, the constellations are not the individual stars or the dot-to-dot drawings. A constellation is just an area of the sky. The whole area of the continental United States is divided into 48 states. The whole sky is divided into 88 constellations. These circled stars are the brightest stars in the constellation of Orion. His stick figure is often drawn like this. It's important to remember, though, that all the stars in this photo are also part of Orion. So this star and this one and these up here are also a part of Orion as well, not just the ones we normally see connected in the stick figure diagrams. Here is another sky map that shows several constellations. Notice that some of them don't show stick figures, while others connect some but not all of the stars. Alternate stick figures you see result from people connecting more or fewer stars in different ways. Notice that in the Ursa Major constellation, the only part included in the stick figure is the Big Dipper asterism. But there are many more stars within the boundary. Ursa Major is the Big Bear, and it's often drawn more fully like this, to include his head, body, legs, and weirdly enough, a long tail. Also notice that some stars have names, like Regulus, while others have numbers or Greek letters for their name, like this star over here, named the Greek letter Pi. A constellation is basically just a bunch of stars that are all in the same general direction. However, it's important to remember that just because two stars look near to one another, they may not be. For example, my parents live just off the same highway I do, but they live almost 2 hours away. The stars in the picture of Orion may all look about the same distance away, but some are many times farther away than others. These two stars at the bottom of the stick figure look relatively close together, but one is only about 100 light years away, and the other is over twice as distant. Asterisms are what people are often talking about when they use the word constellations. Asterisms are created when you make stick figures by connecting the stars of the sky. The Big Dipper, pictured here, is an easy-to-spot asterism that takes up only a small part of the Ursa Major constellation. Similarly, the Teapot asterism takes up only a small portion of the constellation Sagittarius. Earlier in this video, I mentioned that the North Star Polaris appears to hang 30 degrees above the horizon to us here in Pensacola, because Pensacola sits on 30 degrees north latitude. However, depending on where you are on the planet, that will vary. If you were in Boston or Detroit, much farther north, Polaris would be at 42 degrees above the horizon, much higher in the sky, since they are at 42 degrees north latitude. If you were at the North Pole, Polaris would be directly overhead at your zenith. If you were at the equator, which is 0 degrees latitude, you'd barely be able to see Polaris on the horizon. If you were anywhere south of the equator, Polaris would not be visible at all. That also means most stars will spend different amounts of time visible in the sky based on your location. This person is in Pensacola at 30 degrees north latitude. The stars rising and setting along the celestial equator, you can think of these as the stars that hang above the equator, are visible for a long time. A star just rising in the east at sunset would be visible for 12 full hours until set at sunrise. However, a star farther south would follow a much shorter path and may be visible for only a few hours. Polaris and stars that appear to be near it are visible all night for people who live in the northern hemisphere. Polaris is the only one that seems not to move at all. Nearby stars seem to trace a circle as they move around Polaris. Some stars in circumpolar constellations may dip slightly below the horizon for short periods of time, but they would return quickly as the Earth continues to rotate. These are a few of the circumpolar constellations. Perseus, Cassiopeia, Cepheus, and Ursa Major are listed. Draco, which should be in this position, is also a circumpolar constellation. These constellations, or at least parts of them, are visible all year round. This is a more complete image of star trails taken over the course of an entire night, or at least several hours. Again, notice that Polaris is not straight up above your head, which would be about here in this image, but 30 degrees up from the northern horizon. If you make a fist and hold it away from you as far as you can, the width of your fist is about 10 degrees. So if you go 3/5 up from the horizon and look toward the north, you should see Polaris. Don't just face north and look for a bright star. Contrary to popular belief, Polaris is not one of the brightest stars in the sky. In fact, it's barely even in the top 50. This image actually shows two patterns we're looking at in today's lecture. First, as Earth rotates, it moves from west to east, counterclockwise if you're looking down from above the northern pole. This brings the east coast into view of the sun before the west coast, which is why the eastern time zone is ahead of the central and western time zones. Secondly, the tilt of the axis causes the seasons. In this photo, if the sun is off to the right, the northern hemisphere is having summer as it's tilted toward the sun. The southern hemisphere is having winter as it's tilted away from the sun. So what would be different if Earth was not tilted on its axis? I actually already mentioned it. The correct answer is that there would be no seasons. If Earth were not tilted, the climate would be the same all year round. I mentioned earlier that revolution takes about 365.25 days. You'll notice that even that number is rounded. So every once in a while, we actually have to throw in not only a leap year, but even sometimes a leap second has to be taken off in order to keep everything lined up properly. Earth does not revolve around the sun in a perfectly circular orbit. It follows an elliptical or egg-shaped path. This is Kepler's first law. Notice this word elliptical is really close to the word ecliptic that I've used in other lectures we've covered so far, but it is not the same word. You have to be super careful as there are several words in this unit that are really similar. In the picture, you see that the sun is not in the center of the ellipse, but is situated at one of the foci. Eccentricity is a measure of how much an orbit deviates from circular. You've probably heard the word eccentricity before, but probably talking about people, not orbits. If you have an eccentric neighbor, that means they're a little different. Same thing with planetary orbits. The eccentricity value is a measure of how different an orbit is from a perfect circle. A planet with an almost circular orbit has low eccentricity, while an object with a much more oval-shaped orbit is said to have high eccentricity. The closer a planet is to the sun, the faster it moves. This is Kepler's second law. Mercury is closest planet to the sun and revolves much faster than the Earth in only about 88 days. Not only is its orbital path smaller, it's actually traveling at a faster rate of speed. A planet like Saturn, which is much farther away, takes much longer to revolve around the sun. Activate the link given in the PowerPoint to play with the simulation. Because of this elliptical orbit, sometimes the Earth is closer to the sun than others. These two vocabulary words are really important. Perihelion is the point in an orbit where the planet is closest to the sun, and the planet actually travels faster in this point of its orbit. Para means close, and helio means the sun. For Earth, this occurs on about January 3rd. Aphelion is the opposite, when Earth is farthest away from the sun and is actually traveling more slowly. Think A for away. This occurs on about July 4th. Now, this may sound backwards to you, but we are actually farthest away from the sun in the middle of summer on July 4th. And we are closest to the sun in the winter on January 3rd. So it isn't distance from the sun that causes seasons. Do you remember what causes it? Tilt causes the seasons. You can picture it maybe more easily like this. Imagine you're shining a flashlight on this globe. At position A, you're holding the flashlight horizontally, so all the light is focused on that one area. That would be summer. But at position B, you're holding your light at an angle, so the same amount of light is spread over a greater area. That would be winter. The amount of heat and light radiation leaving the sun and arriving at Earth doesn't change, but how it is concentrated does change over the course of a year. Activate the link in the PowerPoint. This animation lets you see how the Earth's position in its orbit and the angle of the sun change over the year from the point of view of this observer. Remember that for the southern hemisphere, the seasons are always opposite of what's happening in the north. Due to Earth's tilt, the sun's path across the sky varies over the course of the year. This is why the length of a day changes over the course of a year. Have you ever noticed that in the summer, it gets light out really early in the morning, but also stays light well into the evening? Whereas in the winter, the sun comes up later and sets earlier? A day is always 24 hours, but the number of hours of daylight changes. In Pensacola, we get 14 hours of light during the summer and only 10 hours of darkness. It's reversed in the winter, so we get less light. The first days of summer and winter are called solstices. The first days of spring and fall are called equinoxes. And we get exactly 12 hours of day and 12 hours of darkness on those days. The equator always gets 12 light and 12 hours of dark year-round. Earth's tilt causes the seasons due to two factors: the number of hours the sun is up and the directness of the rays hitting Earth. Since Earth's orbit is not perfectly circular, sometimes we're a bit closer to the sun at perihelion, and sometimes we're a bit farther away at aphelion. Another repeating pattern we see is what is called the precession of Earth. Earth's tilt changes direction slightly over time. The amount of tilt is the same, always 23.5 degrees, but the direction of the tilt changes. Imagine a child's spinning top. It spins very tightly and remains very stable as long as it's spinning rapidly. But as it slows down, the top starts to wobble. This is what's happening to Earth. Its axis traces a circle in the sky. The North Star actually changes over time. The North Star was called Thuban 3,000 years ago. It's Polaris now, and the North Star will be a different star called Vega in another 12,000 years. This wobble is called precession. Precession occurs because Earth is not a perfect sphere. As it rotates, the planet is actually squashed a bit, making it wider side to side than it is up and down. Looking at the image, Earth is only slightly deformed. The difference between the two radii is only about 20 kilometers. But compare that to Jupiter. Jupiter is much more flattened, and its equatorial radius is over 4,000 kilometers longer than the polar radius. The reason for this deformation is caused by the planet's rotation. Jupiter is more deformed because it's made of gas and it spins much more rapidly than Earth. As the sun and moon pull on Earth, this causes Earth's precession. The change is very slow, but about a degree for every 72 years. So for your entire life and many more generations, Polaris will still be the North Star. But this slow movement does add up over time. The complete cycle takes about 26,000 years. So even though the current pole star Polaris will lose its status when Vega or another star takes over, it will regain it again in 26,000 years and be the North Star again. Now, let's talk about the movement patterns of the moon. The moon rotates and revolves just like the Earth does. It takes the moon about a month to rotate on its axis and almost the exact same amount of time to revolve, which is why we never see the backside of the moon. In fact, the word month used to be spelled M-O-O-N-T-H, moonth. The whole cycle of the moon takes about a month. The moon rises 50 minutes later each day, and the tides are later each day by the same amount. This is because even though the Earth rotates in 24 hours, by the time the Earth finishes that rotation, the moon has moved along its path a little bit. So the Earth needs about 50 more minutes to catch up with the moon's new position. The moon, like the Earth, revolves in an elliptical orbit, meaning that sometimes it's closer to the Earth than others. At perigee, the moon is closest to the Earth and looks slightly bigger. And at apogee, the moon is farther away and looks slightly smaller. Have you ever seen online when the news says there's going to be a supermoon? The moon isn't particularly any more super than normal, but it does look a tiny bit bigger just because it's at the point in its orbit where it's slightly closer to Earth. Notice these two words are similar to the words perihelion and aphelion we talked about earlier. Here, the prefixes peri and ap still mean close and farther away, but the suffix ge refers to the Earth. Geology is the study of Earth. Due to the fact that the moon does not make its own light and is just reflecting sunlight, the position of the moon and sun compared to the Earth allows us to see different portions of the moon's surface illuminated at different times. These shapes we see are called phases. It's important to note that even when we see only a tiny bit of the moon's surface illuminated, half the moon is always reflecting light. It's just that the rest of the lit portion is on the back side of the moon that is facing away from Earth. Remember, the whole cycle lasts about a month. This calendar is old, but I'm showing this January 2014 calendar because the cycle began on the first day of the month. Notice the pattern. For the first 2 weeks, the moon's surface is lit more and more, and it's lit up on the right side. After the full moon, the amount of light we see gets less and less, and it's lit up on the left side. It is important to note that the full moon doesn't always occur mid-month, but the pattern always goes in this order and takes the same amount of time. Activate either of these two simulations in the PowerPoint to see the process in action. I think the first one displays it better, but they're both good. Here, you can see a moon phase model trying to show you two things at once. First, it's trying to show you that the moon is always half lit, whichever side is pointing toward the sun. The phases, though, are caused by the angle at which we're viewing the lit part. We usually only see part of the lit half. Only at full moon do we see the entire lit half of the moon. If you look at the woman in the image, her head is in the position of the moon, with the moon going around her head. If she were to look straight down toward the yellow ball representing the sun, she can only see the unlit side of the moon, what we call the new moon. If she were to look straight up at the moon when it's on the opposite side of the earth as the sun, she'd see the fully lit side, the full moon. The different phases we see are caused by the position of the moon and the sun compared to the earth. You might be wondering why, even though the moon moves around the earth once a month, we don't also get eclipses once a month. The reason why is that the sun, moon, and earth are rarely perfectly lined up. The moon's orbit is slightly tilted compared to the plane of the ecliptic. Most of the time, the moon is slightly above or below the plane of the earth and the sun, so eclipses are much rarer than full and new moons. But when they happen, they can be very impressive. Notice how similar these two words are, and that's because they're related. Eclipses happen when the moon's orbit happens to line up with the plane of the ecliptic. Solar eclipses occur when the moon moves between the earth and the sun, blocking the sun's light from Earth's view. Sol means sun, so solar eclipses occur when sunlight is blocked. This is how a total solar eclipse appears. The moon is in front, but not illuminated from Earth's point of view, because the lit half of the moon is pointing back toward the sun. The fuzzy bit of light you can see around the edges is actually part of the atmosphere of the sun called the corona that we normally can't see because the sun itself is too bright. The moon casts a shadow on the earth. Total solar eclipses are very rare, but partial eclipses like the one we had in 2017 are much more common. Sometimes when the moon is at apogee, it's not large enough to cover the whole sun because it's farther away. So we get something called an annular eclipse. Here's the geometry of it. In a solar eclipse, the moon blocks the light from the sun entirely for a very small part of Earth. That dark shadow area is called the umbra. A much larger part of Earth gets a partial eclipse and is in part shadow, called the penumbra. Notice the order of the objects here. The moon is between the earth and the sun. It is important that you know the order of the objects for each type of eclipse and what's happening in each situation. This shows the view of a partial solar eclipse. Most of the sun is visible, but part is obscured by the moon. People in that lighter penumbral shadow see this. Lunar eclipses occur when the moon passes behind the earth and into Earth's shadow. Luna means moon, so lunar eclipses are when moonlight is blocked. Lunar eclipses actually occur at full moon, but you see that as the moon passes into the shadow, part of the light will be blocked. Notice that the total lunar eclipse, though, is not black, but red. This is sometimes called the blood moon. Even though the moon is in Earth's shadow, the moon still gets a little bit of light that is bent through Earth's atmosphere onto the moon, which causes the reddish color. These lunar eclipses are more common than solar eclipses since the Earth casts a much bigger shadow into space than the moon does. In a lunar eclipse, the moon is on the back side of the Earth as seen from the sun. Sunlight shines on one side of the Earth, but then Earth casts a shadow into space. As the moon passes behind the Earth, it falls into the shadow. Here is a diagram illustrating the difference between the two types. Make sure you know the orientation of the three objects during each eclipse and how the light is being blocked. From Earth's point of view, a solar eclipse looks dark because what we're seeing is the new moon. A lunar eclipse looks reddish from the light being bent through Earth's atmosphere onto the full moon. Click on the link in the PowerPoint for another cool simulation showing eclipses. Eclipses are caused by the repeated pattern of the sun, moon, and Earth's motion that cause shadows to be cast into space and onto other celestial objects. We see eclipses when all three objects line up. It isn't just the Earth and moon that show repeated patterns of motion. This image shows Mars as it appears to travel from right to left across the sky, then moves back to the right, then back again toward the left over a period of several weeks. This looping motion of planets is called retrograde motion. Though the planet appears to move backwards for a while, it doesn't actually change its direction in that manner. It's a trick of perspective from Earth's position. The retrograde motion of planets is explained by looking at the diagram on the left. At position A, Earth looks toward Mars, seeing it in the west. As Earth moves to positions B and C, we see Mars appearing to move east. But since Mars travels more slowly than Earth because it's farther away from the sun, once Earth gets to position D, Mars looks like it's traveling backwards. It's similar to how if you're driving rapidly past a slower car, sometimes that other car seems to be moving backwards. Earth passes Mars at a higher rate of speed, and it makes Mars appear to be moving backwards. Visit the link in the PowerPoint to view an animation that demonstrates this motion. If you activate this video, you can see the difference in speeds of the different planets, demonstrating Kepler's second law, and some of the planets going through their retrograde motion. Another pattern we see involves the planet Venus. It has phases similar to the moon, but notice that the crescent phases of Venus appear larger than the gibbous phases. That's important. The reason crescent Venus looks larger than the gibbous phase of Venus is because Venus is closer to us when it's in its crescent phase than it is in its gibbous phase. Click on the link in the PowerPoint to see a great animation of how the relative positions of Earth and Venus create Venus's phases. Stars appear to move across the sky as a group, but planets change in position relative to the stars. Planets exhibit retrograde motion. That is, they appear to change direction in looping patterns as they move across the sky. Stars do not do this. Finally, let's look at a couple of patterns we observe in stars. If you've ever looked closely at a star map, you may have noticed that some stars have strange-sounding names. This is true for a variety of reasons. First, many stars were named thousands of years ago by Arab astronomers. They were the best astronomers at the time. Many other stars are named in Greek, and we'll see some of those later. So if the only language you speak is English, a lot of star names will appear strange to you. Some stars have names that describe the star itself or where they are in a particular constellation. For example, Deneb is the star in the tail of Cygnus the Swan. Antares is a bright red-orange star that looks a lot like the planet Mars. Antares literally means rival of or anti-Mars. Mars is the Roman god of war, and Ares was his Greek counterpart. The star is named this way because if you're not careful, it's easy to mistake the star Antares for the planet Mars. I won't expect you to memorize these names and what they mean, but I do want you to recognize the fact that some stars are named in this way. Many stars are simply given a Greek letter as their name. The Greek alphabet's first 4 letters are alpha, beta, gamma, and delta. So the brightest star in a particular constellation is often given the name Alpha. The second brightest is Beta, and so on until you run out of Greek letters. These are the most common names you see on star charts today. In addition to the Greek letter, the star has to get another designation to tell you which constellation it's from. This is because every constellation has an alpha and a beta and a gamma star and so on. So the Greek letter is like the star's first name, and the possessive form in the constellation is like the star's last name. In this example, the brightest star in the constellation of Centaurus is called Alpha Centauri. Similarly, the second brightest star in the constellation Gemini would be Beta Geminorum. The first name rates the brightness. The second name identifies which constellation it is found in. So let's look back at the map we looked at earlier. There are several stars that each carry the Alpha designation. Each one of these stars are the brightest one in their respective constellations. This one is Alpha Ursa Majoris, while this one is Alpha Leonis. You don't need to memorize all the Greek letters, but you should know the first few letters in order. Alpha, Beta, Gamma, and Delta, as these stars are the brightest ones in each constellation. Here is another example showing 2 images of the constellation Orion. Alpha Orionis and Beta Orionis are the 2 brightest stars. They also have the more commonly used names Betelgeuse and Rigel. In the photo, you may notice that Rigel appears even brighter even though it carries the name Beta. But it's likely that this star was less bright compared to the Alpha star at the time when it was named. In addition to their names, another important thing you need to know about a star is its magnitude. Magnitude is a way to compare the brightness of stars. Early astronomers called the brightest stars first magnitude stars. This is often abbreviated as Mag 1. Slightly dimmer stars were called second magnitude stars, or Mag 2 stars. Stars even dimmer than that were called third magnitude, and so on. The larger the magnitude number, the dimmer the star. A dorky way to help you remember that is the bigger the magnitude number, the bigger the telescope you'll need to see it. Stars with a higher magnitude than about 6 cannot be seen without a telescope. This scale is called apparent magnitude, and it's how bright stars appear from Earth. Later in the course, we'll talk about another brightness scale that isn't dependent on a star's position relative to Earth. The numbers that were originally assigned to stars have changed a little over the last few hundred years. Based on this mathematical refinement, the bright star Sirius in the constellation of Canis Major is actually a magnitude -1. That means it's very bright. Planet Venus is even brighter. The full moon and the sun are much brighter still, thus having numbers even farther to the negative side of the scale. The Hubble Space Telescope is capable of seeing stars as dim as magnitude 28. That is much too faint for telescopes on Earth's surface. The James Webb Space Telescope goes out to magnitude 34. You don't need to memorize any of these numbers, but this chart is a handy way of quickly comparing the numbers and objects that are easy to find in the sky. When comparing star brightness, small magnitude numbers indicate brighter stars. Larger numbers indicate dim stars. You cannot directly tell the size of a star by its brightness, but many star maps use a bigger dot to indicate a brighter star.